So good morning, everybody. Welcome to my home. I decided to work from home today. So right now we're in my basement. So I think we might as well get going. Let me just share my screen here. I was just out for a little walk and it's a nice, beautiful day outside today. Just go to here. Oop. Hopefully everybody can see that okay. Yeah, so today I want to talk about solving dynamics problems in 2 dimensions. And also we're going to get into projectile motion, which is section 4.5. And I thought I would start with a poll. If everybody can see this, just make sure we got chat and participants. Yeah, so have you tried this module 4 pre-class quiz? Let me launch this poll. So if you say A, you haven't tried it yet. So the good thing to keep in mind is it's due today at 8:45 p.m. So leave yourself a little time to do that in the next 8 hours. Yes, B is yes, it went fine. C is yes, but there was some issues with either, knowing what was expected of you in the physics sort of side of things. And D is yes, but you had some sort of technical issues like a slow upload or something like that that's concerning you. So I'm interested to see how that's going so far. Oh, someone mentioned that you're having a little trouble with volume, so I can try to speak a little louder. This is a bit of a different environment, and so I'm trying to get used to it. So I appreciate hearing about the sound issues. Okay, let's stop the polling since 93% of you have voted. And so most of you, it says 49% of you have not yet done this quiz, which is fine. It's based on the friction stuff. So it's the exact same format as midterm assessment 2. Midterm assessment 2 will be 2 questions of exactly this difficulty level, but it will cover all of chapter 4, whereas both the questions in this chapter 4 practice quiz are really on this this friction stuff that we talked about on Friday. So 28% of you, it looks like it went okay. 20% of you are kind of a little worried on the physics side, and 8% of you had some technical difficulties uploading it. So that's what that looks like. So that's a bit concerning. 40 of you had those problems. So I just want to mention a few things. So on Tuesday, October the 13th, from 8:10 to 8:40 Toronto time, you'll need to upload 2 solutions into a quiz very similar to the chapter 4 practice quiz, meaning that you'll have to have that sheet ready, the answer template sheet with the 4 different sections, and write out the solution on 1 piece of paper about that size. So you can print these out beforehand and then just write it out. You'll see the question coming from the quiz. You don't have to download anything during the quiz. You just have to write out your answer, and then you just have to upload the image. And I was able to do this on my phone, just click upload image. You have to do them 1 at a time. So really try to do 15 minutes per question and then upload it, and then you'll see the next question. So I am going to try, in case of weird Quarkus related glitchiness, I have set up a Google Drive folder, which is already open. It's called the Physics 131 Midterm Assessment 2 Last Resort folder. So this link will be available in the instructions in case, for whatever reason, if you're having trouble uploading to Quarkus and you're starting to feel a bit panicky about that, you could just dump it into the Google Drive folder and then just move on. And that way we'll have a time stamped file for you that we can try to sort out later. So you don't waste a lot of time just with a Quarkus thing swirling around there. But hopefully it shouldn't have too many problems. Let me look at some of the questions on the screen here. Yeah, I'm not going to increase the amount of time. I think half an hour should be enough time to do these. We'll see how it goes, right? Someone says I'm cutting off. That's not good. Maybe my internet in my basement here is not as good as before. Does that work? Maybe Wednesday I'll go back to my regular setting there. Some people say it's okay. All right. So someone asked us if there's going to be a chapter review in Mastering Physics. So I think just the homeworks that I've already posted on Mastering Physics should be enough review for you between now and Tuesday afternoon. So there's a lot of questions and they're all from chapter 4. They're all at the right difficulty level. If you can get through your Mastering Physics homework, I think you'll definitely have enough practice for this midterm coming up. It is difficult homework, but it's at the right level for it to prepare you for the quiz. And actually, Mady, did you want to ask a question? Hands up.
Hello.
Hi.
Hi. Just was wondering because like I don't see the chats from other people. Is that like for everyone or it's just the case for me?
The chat?
Yes. Like it's just when I'm trying to send a message only to the panelists, it's not like to everyone or anything.
Yeah. So when I have set up the chat on purpose that way so that it's just only that I can see it. So sorry about that.
Okay.
That's
No.
just. And then Florence, did you want to have a question?
Yeah, I had a question about vector signs for forces.
Yes.
So in my high school, when we were doing the F equals ma, we didn't write the vector sign over the F's because we put the sign in front already. Like we put negative F without the vector sign. So will it be marked wrong on the midterm assessment or on the test if we do that?
No. In fact, I think that's a really good question. I think that's right. So you do have to put the little arrows on your symbols when you're setting up your force diagram, which is for that second step. Try to remember to put those on there. That's important because you're drawing vectors in that case. But then you set up an X and Y axis. And when you actually write out your equations, you're really just writing out the X and Y components. Those are not vectors. So I think it's actually better not to put the vector symbols on the symbols that are in your equations that you're writing out.
Okay, thank you.
So I think you're doing a good job there. That's great. Okay. Let's go on to my slides here a bit more. Some great questions and comments there. Oh yeah, so I did have a little quick demo I wanted to do down here on my ping pong table where I happen to be, but this is a plot of the friction force versus time when you're increasing the force on an object. So you have an object, a mass here, it's sitting on a table, and you are applying with your hand or something an outside force. So there's some sort of applied force that you would push on it in one direction on the block. And then there's going to be from down here sort of a frictional force of the surface on the block, right? This is the block B. And that friction force will adjust itself to be equal to F is equal to this F applied or something like that. They'll be the same magnitude for a while because it stays stationary. But then it gets up to this maximum value, which is mu sub n times mu sub s times this normal force n. And then it quickly drops down as the thing starts moving. And then you've got this constant frictional force, which is equal to this mu sub k, the coefficient of kinetic friction, again, times the normal force. And if you have a mass on an incline, for example, I can try to draw the force diagram. If we call this M, diagram of M. I'll show you the way I normally draw it. So what do we have? We have, there's the dot. We're going to have the force of gravity of the Earth on M, and don't forget your little arrow. What else do we have? Well, we have the normal force, and the normal force will be perpendicular to this surface, right? So that'll be at an angle of the surface on M. We can put an arrow in there. And then the other thing that we're going to have, if it's moving or even if it's not moving, is that there will be a friction force pulling it backwards. So I'm going to draw that. And the friction force is always perpendicular to the normal force, because the normal force is perpendicular to the surface and the friction force is parallel to the surface. So I'll write that F here of the surface on M. And I don't really know yet if it's kinetic or static, because I don't know if it's sliding or not, but I do know that's the direction. So don't forget to put that on there. And then the other thing you have to do is define X, Y axes. And you could do it like this. You could do Y up and X to the right, in which case the gravity force would be in the negative Y direction. And these forces would have their diagonals. But what you can do, what I'm going to do is, that's one way of doing it. I'm going to define my axes to be tilted. This is what I like to do. You can do it both ways, and then both ways you can solve problems. But if you define the y-axis being perpendicular to the surface and x-axis along the surface, then gravity turns out to be the diagonal force. And gravity is actually a thing that's dragging it in the plus x direction. And if I stop the share for a sec, so there's me again, and we look at this little mass and an incline. What I can show, so here's a mass, here's a little surface. If I tilt it up, then we have static friction, which is holding the mass on the surface. And the more I increase this incline, the more the x component of the gravity increases. So there's a negative x component of the friction force, which is keeping it on the surface until up, and we get to some point, and then it starts accelerating because you've gone past this maximum angle, the maximum static friction force, and then once it starts moving, you get into the kinetic friction. And now it's sticking to the wood. I think what's going on here is that the surface of the wood, between the wood and the mass, is a higher coefficients of friction than this slippery kind of placemat thing. So once it gets to the wood, it slows down a lot and stops. And so you can go to a greater angle there. But this is actually how they measure a lot of these coefficients of friction, is they actually will put two objects together on an incline and increase the gravity until they measure that angle. And then you can use that angle to solve for what the coefficients of friction are. Okay, let's go back to the slides here. Okay. Yeah, so I want to talk quickly just about some of the skills that are involved that you have to write down in your force questions, like you'll get on the midterm assessment too. So the first step is sketch and translate, should be on your page. What you're doing there is you're making a quick sketch of what you think is going on, what the most important things are. And your artistic, skills here are not what you're getting marked on, but just trying to draw like a box or showing what you think is happening. You choose a system that you're going to be drawing force diagrams for. You choose a coordinate axis in this step, like that x, y. One axis should be in the direction of the acceleration. That's my recommendation. That way, the other axis shows a direction in which there's zero acceleration, and that gives you a nice simple formula for that. Indicate on the sketch everything you know about the process relative to these axes, like you're putting on your knowns and unknowns. You identify the unknown quantity of interest. So you write down what are the variables that are given and what is the variable that is asked for, kind of make a list there. Next step for the next 2 points is the simplify and diagram step. So in that step, you're trying to say what it is you're simplifying, what it is you're modeling. So for example, you might be ignoring friction. You should write that down. Let's neglect friction or something here, or air resistance. And then you want to draw a force diagram for these chapter 4 problems. And, you know, look at the diagram, see if they make sense. The next step is going to be your represent mathematically step. That's where you're actually writing down, usually it's Newton's second law. You'll have Newton's second law will be 2 equations, because you'll have Newton's second law in the x direction and Newton's second law in the y direction. And then your last step is your solve and evaluate. You only get two points for this solve and evaluate step. So this is where you actually write down the right answer, right? You substitute the given values into the mathematical expressions you've solved for. And then you look at your assumptions, were they reasonable? And look at the final answer. Check the units, maybe check limiting cases, and see whether the answer has a reasonable magnitude. And I think maybe to kind of get us started on this, before I go to questions, I realize that none of you have raised hands, but let me go through an example. A cart of mass m is on a track, which is at an angle of theta above the horizontal. The cart is attached to a string, which goes over a pulley, and the other end of the string is attached to a hanging mass m. What is the acceleration of the cart? Let me just actually take a quick look at what's going on here. Okay, so sketch and translate. So in this case, rather than having one system, I think we have 2 connected systems. So I'm just going to write that out. And that's often the case when you have like a tension for a string. It's between 2 different objects, right? So there's one right here, which is the capital M. And there's one over here, which is the lowercase m. And so here's this one. It's got some wheels on it, and it's being pulled upwards by some tension. This is, I'm going to call it the cart, see? And then this one, the hanging mass, which is being pulled upwards by the tension, I'm going to call that little m, mass. And the mass of cart, this is a bit weird of notation, but the mass of the cart is an uppercase m, and the mass of the little hanging mass is a lowercase m. And the idea here is that the acceleration magnitude is the same for both objects, for both systems, as they are connected by a string that does not stretch. Does that make sense? So as one of them moves, the other one will move. If one moves like 2 centimeters down, then the hanging mass moves 2 centimeters down, the cart will move 2 centimeters up in that same amount of time. So their motion matches each other. So you'd expect them to have the same accelerations, even though they're 2 different systems. And once again, whenever I go to a demo and then I go back to, there we go. I lose my lists here. Okay. So simplifying diagram step. I'm going to draw 2 diagrams now. I'm going to actually, first of all, I'm going to assume no friction on the cart. It doesn't really say that, but I don't think I can really solve this. See that? It says on a track. I'm going to assume 0 friction on the cart. So let's draw the cart force diagram. So what it's going to have is going to have a tension up the hill, tension of the rope on the cart. It's going to have gravity pulling it down, the force of gravity of the earth on the cart. And then a normal force, which in this case is perpendicular to the tension of the normal force of the surface, surface on the cart. And the acceleration is is that way. I'm going to, I guess, tilt my axes here. Define, as I did before, y to be up that way and x to be that direction. So a in plus x direction. And I'm also going to, so what that's going to do is it's going to make gravity the diagonal force. So the diagonal force is gravity. So I'm going to have to do that carefully. Here's your F, oops. The arrow is going down, so let's draw that again. Here's your gravity, F sub G. It's always a little hard with these angles. That's your theta right there, right? So the way I try to do it is I remember that this is theta. So if there is an angle here, which will be your negative F sub Y of G, then this angle right here is 90 degrees minus theta. And so this angle right here is 90 minus theta, so it's theta. And there's your right angle. This will be your negative FG in the x direction. And so the way my angles work out here is that the sine of theta is negative F sub x over FG. And the cosine of theta is negative F sub y over FG. So I'm going to need those when I start doing the Newton's second law for the cart. And I will be posting these notes, but I'm going to have to, I can go back to it in a minute, but let me just go to the next slide. I still haven't done the force diagram for the hanging mass, so I have to do that still. Let's do the hanging mass. So it's like this. Here is the tension of the rope on little mass. And here is the force of gravity of the Earth on the little mass. I'm going to, in this case, I'm going to define, I might as well just define plus x equals down. There's a lot of ways that you could do this, but this will allow me to just use the same acceleration before, because as the cart goes up the hill in its plus x direction, the mass is going to go down the hill, right? So this is so that A for the little m is the same as A for the cart. And there's no diagonal forces. There's not much I have to do there. On represent mathematically, let's do the cart first. I've got the x component, the y component, and then there's these three forces. There's the normal force, the tension force, and the gravity force. So let's just try to keep track of our components. The normal force is just in the plus y direction. Let's go back and check that. Yeah, the normal force was in the plus y direction. And the tension force was in the plus x direction. So we'll just put t here and 0. And then the gravity force was negative capital M times g times sine theta for the x direction and negative mg cos theta for the y direction. That's how we set up our thetas there. So there's no y acceleration of the cart. That's why we set the y axis in that direction. So what that means is that the sum of forces in the y direction equals 0. That's going to be equal to the normal minus m times g times cos theta. So the normal force equals m times g times cos theta. I don't actually think we need that here. But anyway, it's good to have it. Also, a sub x is going to be equal to the sum of the forces in the x direction divided by capital M for the cart. You're going to have t minus mg sine theta divided by m. I'm going to call that equation 1. And then for the hanging mass, what we've got is a sub x is equal to the sum of the forces in that x direction, which I've defined as down, divided by lowercase m, because that's the mass of the hanging mass. It's little mg minus the tension, all divided by little m. We can call that equation 2. So we have two unknowns and two equations. The two unknowns are acceleration and tension. We need A. That's what we're asked for. We don't care about the tension. So what I'm going to do, T, is solve for T in 1 and then plug in. And that'll eliminate the T. So sorry, we're just going to go to the next step here. So use 1 to solve for the tension. I get, remember it was A is equal to T minus capital M times G times sine theta divided by capital M. I'm going to solve that out. I've got M times A is T minus capital M times G times sine theta. So T is equal to mass times A plus G sine theta. I'm going to plug into equation 2. And that'll eliminate the variable I don't care about T. So equation 2 is A is equal to, what was it? Mg minus T over M. And those are lowercase m, so Mg minus T, which is capital M times A plus G sine theta, all divided by lowercase m. So A is equal to, just solving that out, G minus capital M over M times A minus capital M over lowercase m times G sine theta. It's just a bunch of algebra now. A is equal to, let's gather all the terms with A on one side of the equation. So I've got A plus capital M over lowercase m times A is equal to G times 1 minus capital M over M sine theta. And then I can pull out the factor of A, 1 plus capital M over M is equal to all that stuff. So I end up with A is equal to G times this big thing, M minus capital M sine theta divided by M plus M. So that's sort of my answer. I wasn't given numbers, so you can't really display a number here, but I can check a few limits if I want to evaluate this. If the cart is much, much more massive than lowercase m, then A is just going to be equal to negative G sine theta. It's going to roll backwards, and that kind of makes sense. Rolls backwards. Also, if theta equals 0, then A is equal to G times little m over M plus M. It's gonna, the whole thing will accelerate that way. And then also, if in theta 0 and little m is much, much greater than m, then A is equal to plus G. And so that's the case where you've got a very, not very massive cart, but a more massive hanging mass, then A is equal to plus G. It's just gonna pull it down. Okay, and then I'll kind of go through just these. So first thing I did was make a sketch, then 2 force diagrams, one for the cart, one for the hanging mass, solve it out. The acceleration was the same for both. And the tension was the same for both. It's the same string. And so I was able to eliminate one of them and solve for the answer. So let me go up here and see what people are saying. Yeah, why can't we treat the whole thing as a system if the acceleration could be the same for both of them? That's a good question. I think you could do that. Just draw a dashed line around the entire thing. The only thing is you have to be a little careful there because the system, part of the system is going down and part of the system is going left and right. So I find that a little harder, but if you can work it out that way, Hamad, that'll work for me as well, as long as you're careful. Friction is neglected. Arshia asked a good question there. I said it somewhere in one of my steps, to neglect friction on the cart. Assume there's no friction on the cart, so that was just an assumption. Good point. Yeah, Sunny Wu asked, isn't the little hanging mass accelerating in the y direction? So I can define different axes for the two different systems, and I just decided to define the plus x as being, you know, in the vertical direction. So, and Ariba asked the same question. Why did I do that? You didn't have to do that, but the point is that you do have to at some point make the realize that the cart acceleration in its direction along the track is the same magnitude as the downward acceleration of the hanging mass. So however you define your axes, you do have to say that that acceleration is the same for both objects. What's next here? I think next we're just going on to projectile motion. So we have a little bit of time here, which we are covering in this course. Ilian, did you want to unmute?
Hi.
Hi.
Would you be able to go a couple slides back to the, or I guess maybe it's just one slide back with the diagram for the cart?
This one?
Yeah, I was just kind of, I mean, I might have it wrong, but I was kind of just thinking, because so you made the x-axis parallel to the ramp, right?
Yes.
So, So, okay, would you be able to, sorry, would you be able to clarify with the force gravity part of it with the angle?
Yeah, sure.
Okay, sorry, thank you.
Yeah, that's okay. It's a good question because, you know, normally you set y to be equal to, you know, the plus y direction. Gravity is in the negative y direction. So the trick with any problem where you have a track or some direction where the object can accelerate in a diagonal direction, I mean, you can do it in a number of ways. You can do these problems. You can keep y being vertical if you want, but I always find it much easier to actually tilt your coordinate axes. So that the reason I do that is so that, why do I do that? I do that so that there's no y component of the acceleration. All the acceleration is along the track. So if you know it's not accelerating like away from the track or into the track, then you get a whole other equation that way really easily. Otherwise, if you keep your axes, you know, vertical, like the way you would normally do it, then your gravity would just be in the negative y direction, but you'd have to do components for the normal, components for the tension, and components for the acceleration. So you end up with a lot more kind of complicated looking equations that don't sum to be zero. So the trick here is tilt your axes. The plus side is that now the normal force and the tension only have one component. And also the plus side is that the acceleration only has one component. The other, the y component of the acceleration is zero. The downside is that now gravity is on the diagonal. And so, but that's okay. You just have to carefully draw out, as I've done here, the force of gravity and then decompose it into its two components. So you now need two components, one of which is parallel to y and one of which is parallel to x, which sum to be the gravity. You need two perpendicular components when you add them together like vectors, that they give you the hypotenuse, and the hypotenuse is the actual force of gravity. So this just takes some practice, and you're going to have to decompose vectors like this, you know, whenever you have a tilted axis. But when there's acceleration that's along the track, I would do it for the gravity, as we've done here. That's a great question. So what time is it? I've got 11:44. I wanted to spend some time talking about projectile motion. So I've got my angry bird once again. And this idea is that when something only has one force acting on it, which is gravity, and it's flying through the air, then it has an acceleration, which is negative 9.8 or 9.8 towards the center of the Earth. And the trajectory is a parabola. So we'll do a quick poll here. See what you guys think about this. At time 0, ball 1 is dropped. Simultaneously, ball 2 is shot horizontally when a compressed spring is released. Which ball hits the surface first? Oops, wrong. Let's press the wrong button. Is it A, ball 1? Is it B, ball 2? Or is it C, both will hit the surface at the same time? Just give you another 15 seconds to click in on that. Okay. And let me just take your answer, show the results. So 79% of you are voting for C, both hit the surface at the same time. That was actually the one I liked. And then there is ball 1 or ball 2. So certainly ball 1 travels a much shorter distance. It goes straight down. But what I'm trying to say is that they both take the same amount of time. So my idea here, so the answer is C, is that both, if you set up an axis like this, where y is up and x is to the right, both balls travel the same y distance. They have to travel this distance y, and they both start with the same v sub 0 y equals 0 for both balls. That is because first of all, ball 1 was dropped from rest, and ball 2 was shot in an exactly horizontal direction. So it was given a large initial velocity, but it's all in the x component, and the y component is 0. So in that sense, if you just look at the y motion, it's like they were both dropped from rest. So it's this amazing thing that if you take a bullet and you hold it in your hand, and you take a gun and you fire it, and you do that at the same time as you drop the bullet, both bullets will hit the ground at the same time, assuming you're on flat ground. It's just the difference is the bullet you shot lands on the ground way, way, way over there after, passing through whatever happened to be over on that side. But, bullets don't stay in the air very long. They just go very fast horizontally. So the whole point here is that projectile motion is made up of 2 independent motions. It's uniform motion at a constant velocity in the horizontal direction. This is your x. And it's free fall motion in the vertical direction for your y. And what you do is with your equations, you just set up everything in the x components, set up everything in the y components, and the common shared variable between them in this case is time. So, and another way of trying to convince you of that is think about this. If you are standing perfectly still and you take a basketball or a bird or something, you throw it up and it goes down, you catch it again. And so you've got this y motion. If you are on roller skates and you are just cruising along at a constant velocity in the plus x direction, you can do the same thing. And you can imagine maybe you're in a car and you're going along the highway at some really, really fast speed, but you're inside the car and you're in the back seat, so you're not driving, and you throw it up and catch it again. It's fine to do that. But what's happening is that in the lab frame, what's happening is that the ball is going in this big parabolic trajectory. You throw a ball straight up while standing in a fixed position, it goes up, stops, and then comes back down. If you're moving, then you've got that same y motion up and down, But on top of that, you've got this constant plus x velocity for the whole time. I think I have another. So what it looks like is this. Let's say, just to put some numbers on it, if you start your projectile with some upward component of 19.6 meters per second and a sideways component of 19.8 or 9.8 meters per second, we just chose those numbers, then every second of time, what will happen is that the y component will decrease by 9.8 meters per second So 1 second later, it'll be up there. 1 second after that, the y component will have gone to 0, but it'll still be moving in the x direction with 9.8. And you can notice this 9.8 in the x direction never changes, just keeps going. But what happens in the y component is it goes down by negative 9.8 every second. So 1, 2, 3, 4 seconds later, it's returned to the same vertical position, but it's now way over in the plus x direction. Let's do another quick poll here. A tennis ball is launched at an angle and it flies through the air in a parabolic path as shown from A to B to C. At point B, let's launch a poll here. Is it that the velocity is horizontal and the speed is maximum? B, the velocity is horizontal and the speed is minimum? C, the velocity is horizontal, but the speed is neither a maximum nor a minimum? D, the velocity is not horizontal, but the speed is minimum? Or E, the velocity is not horizontal and the speed is neither a maximum or a minimum? Nice little conceptual question here. I'll let you think about that. Give you another 10 seconds or so to think about this and see what you think, and I'll discuss. Okay. So let's end the polling, share the results. 53% of you answered B, that the velocity is horizontal and the speed is minimum. And then the other 31% of you, second most popular choice is that the velocity is horizontal and the speed is neither a maximum or a minimum. So what I liked was B. Oops, okay. I liked that. The velocity is horizontal. So here's the velocity at the beginning. It's on a diagonal. At the top, the velocity is always at the, I drew it a little too long there, but the velocity is always a tangent to the path, right? So what I'm saying is that I think it's going slowest at the top of its path and then it's coming and speeding up again. And the reason is that so the x component is always the same. So that doesn't change. The x component of velocity is neither at a maximum nor a minimum when it's at the top. But there's a y component that starts off going up and ends up going down, but is 0 right here. So if you kind of think of your Pythagoras as being the actual velocity is the hypotenuse, and the components, like the square root of the sum of the squares of the components gives you the magnitude of the speed, right? So if the y component goes to 0, your speed is minimum. Okay, so as you go up, it slows down, gets to some minimum speed, which is not 0, and then it speeds up again on the way down. So it slows down, speeds up, just as you would if it was going straight up and down. It's just that when it's going straight up and down, the speed at the top is 0. If it's got an x component, then the speed at the top of that whole path just goes to a minimum. What time is it right here? About 6 minutes. So here's some equations. This is just showing that the x component of the velocity, oh, there's my kids home for lunch, is v sub 0 times cos theta. The initial y component of the velocity is v sub 0 times sine theta, usually. That's when you set it up as I did in that other previous diagram. Here's your v sub 0, and here's your theta, and here is your x component, x in your y directions. And then, yeah, the y position is just the y initial position plus v0 in the y direction times t minus 1/2 gt squared. So what's happening is that the acceleration in the y direction is negative g, and the acceleration in the x direction is just 0. And let's actually, I think I have time for a quick example. So let's go through this. Here's problem 4.60 from your new homework. An airplane is delivering food to a small island. It flies 100 meters above the ground. So let's draw an airplane. And this is 100 meters. And it flies at a speed of 160 meters per second. And here's an island over here. I'll draw a little palm tree island. Where should the parcel be released so it lands on the island? So I think the parcel is going to start with the same speed as the plane. So parcel, let's see, parcel has same initial velocity as the plane, and then it drops. And so what we're trying to find here is x, find x. And v0y equals 0 when released. I'm going to assume that. Released. So I'm also going to neglect air resistance, which is sort of a iffy thing to do here. And a sub y is negative 9.8. Should probably plug in my headphones pretty soon here. So v sub x is going to be x divided by t. I'm going to call that equation 1. And y is going to be v sub 0y times t plus, I'm going to actually define, by the way. I'm going to define y is down and x is this direction. So it's plus 1/2 gt squared. I'm going to call that equation 2, and I'm going to solve for x. And the idea here is you have the same t for both. As I mentioned before, the linking between the x components and the y components is always going to be the time. So I can quickly just show you the way it's going to look. So x is equal to v sub x times t. You need the t. I don't have it. So from equation 2, you've got y is 1/2 gt squared. So 2 times y over g is t squared. So t is the square root of 2y divided by g. So then you plug that in to here. X is equal to v sub x times the square root of 2 times y divided by g. So I can write that as 160 times the square root of 2 times 100 divided by 9.8. So x is equal to 722.8. I think there's really only one sig figure here, one significant digit. So x is equal to 700 meters. Okay. Seems like a long way if you're only dropping at 100 meters, but you've neglected air resistance. So I think it seems okay. So before class 12 on Wednesday, I would like you to finish reading chapter 4. We're going to be discussing a bit about rolling without slipping, and we're going to be taking up chapter 4 problems. On Friday, we're going to start in on chapter 5, even though chapter 5 material will not be on this midterm assessment on October 13th, but I want to start in on it. And also on Friday, we're going to be doing a group quiz during class. So you should be able to work with your practicals partners in Microsoft Teams. So everyone who is the most recent facilitator has to go on Microsoft Teams and call up a meeting with your practical group during the Friday class. And we're going to have a little team up quiz that you can share the mark on during the Friday class, just to get people talking to each other during class. And the Monday there's no class, and then on Tuesday we have that midterm. So what I'm going to do is I do want to take your questions. I can see that there's 19 people with their hands up right now, so I want to take those questions. I'm going to turn off the recording, and I'll see the rest of you on Wednesday. So let's stop.